Greetings, everyone. In this video, I'm going to introduce the independent samples test for proportions, also known as the two-proportion z-test. This is a statistical hypothesis test used to determine whether there is a significant difference between the proportions of a certain characteristic in two independently selected samples from different populations. As always, I'll demonstrate the steps using an example. Let's say the Office of Institutional Research at a small college wants to find out whether the proportions of first-generation college students are the same among male and female freshmen. A total of 1,231 students were included in this study. Among them, 381 are boys and 850 are girls. The number of first-gen students in each group is 64 and 110, respectively. Our goal is to test whether the proportions of first-generation students are the same in the male and female freshman populations. So let's start by setting up the hypotheses. The null hypothesis says that P1 equals P2, meaning the proportions of first-generation students are not significantly different between male and female students. The alternative hypothesis, HA, is P1 not equals P2, which states that the proportions are significantly different. Remember, these capital P's represent population parameters, not sample statistics. Now, step 2, we'll use alpha equals 0.05. The sampling distribution of P1 minus P2 follows a binomial distribution. When the sample size is large enough, we can approximate it using a normal distribution. The mean of this sampling distribution is P1 minus P2, and the standard error of the difference between independent proportions is calculated as the square root of P times Q times the sum of the inverses of the two sample sizes, N1 and N2. Here, P represents the overall proportion of occurrence in the two samples combined. That's the total frequency of the characteristic divided by N1 plus N2. And Q is simply 1 minus P. Moving on to step 3, let's plug in the numbers. We know that P is 110 plus 64 over the total sample size of 1,231. This gives us P equals 0.141. Then Q equals 1 minus 0.141 equals 0.859. Now we can calculate the standard error, which comes out to 0.022. Next, we find the sample proportions. For males, P1 equals 64 over 381 equals 0.168. For females, P2 equals 110 over 850 equals 0.129. The observed difference between the two proportions is 0.168 minus 0.129 equals 0.039. Since the hypothesized difference between the two population proportions is 0, we can calculate the observed z as 0.039 minus 0 over 0.022. which is 1.796. Looking this up in a z-table gives a p-value of 0.073. Because p equals 0.073 is greater than alpha 0.05, we fail to reject the null hypothesis. You can reach the same conclusion if you compare the observed z-value of 1.796 with the critical z-value of 1.96. So given alpha equals 0.05, the researchers at OIR concluded that the proportions of first-generation college students are not significantly different between males and females. Now let's construct the 95% confidence interval. It's the difference between the two sample proportions plus minus the critical z-value times the standard error. That's 0.039 plus minus 0.043, giving a range from negative 0.004 to 0.082. Because 0 false within this interval, it supports our earlier decision to retain the null hypothesis. As you can see, this test involves several calculation steps and formulas. But things get much easier when you use SPSS. Here is how you can run independent samples test for proportions in SPSS. Open your dataset, go to Analyze, Compare Means and Proportions, then choose Independent Samples Proportions. Use sex as the grouping variable and generation as the test variable. You can choose different tests, but the default WALD H0 works just fine. Click OK. In the output, the first table, Independent Samples Proportions Group Statistics, shows the sample proportions P1 and P2. The third table, Independent Samples Proportions Test, includes the difference in the proportions, the standard error, the z-value, and the p-value. The second table, Independent Samples Proportions Confidence Interval, gives the CI. Before I let you go, here's some food for thought. We've been saying that inferential statistics are based on samples, and our conclusions are built on probabilities. But what if, in this case, we actually had data for the entire population? Would we still need to run a test of significance?